Hello everyone, welcome to the last video in this series. We start with problem number 91. A rubber band is stretched up to 1.1 times of its original length isothermally. Its entropy will decrease because the entropy delta S is equal to dq by T, and when you stretch the rubber band, heat is produced. That means dq is negative. So delta S is also negative, but we need more information to calculate the entropy change quantitatively. So I'll leave it as it is. Problem number 92. An ensemble of n 3-level system with energies E equal to minus epsilon 0 and plus epsilon is in thermal equilibrium at temperature T. At high temperature, the free energy is approximately. So let us first calculate the partition function. Z is equal to e to the power minus beta epsilon naught plus e to the power plus beta epsilon naught plus 1. This is essentially e to the power 0. So which can be simplified to 1 plus 2 cos of beta epsilon naught. Now the free energy is defined as F is equal to minus kT ln Zn, since we have n particles, and this is minus k t n and log of 1 plus 2 cos of beta epsilon naught. So we have to expand this. So let us do that. So note that cos hyperbolic x, so here x is beta epsilon naught, has the series expansion as 1 plus x squared by 2 plus other. So we have log of 1 plus 2 cos x, and this is approximately log of 1 plus 2 1 plus x squared by 2, which is log of 3 plus x squared. And now I can take 3 common and write it as 1 plus x squared by 3, so which is 3 log 3 plus log of 1 plus x squared by 3. And now we expand this, and the final answer will be log 3 plus x squared by 3. So let us go to the options. So option C is the correct answer. Problem 93. N identical fermions occupy n plus 2 states in 24 different ways. The value of n is, so we have n fermions and n plus 2 states. So the number of possible way is n plus 2 Cn, and this is equal to n plus 2 factorial divided by n factorial 2 factorial. So this is essentially L plus 2 n plus 1 divided by 2, and this is equal to 28, and the solution for n is 6. So option D is the correct answer. Problem number 94. The thermodynamic relation expressing TdS equation is. To derive that equation, we start with the following: S as a function of T and V. Now we take the differential. ds is equal to ds by dt with v constant times dt plus ds by dv with t constant dv. Now multiply both sides by t, and this can be related to cv dt, which we are not interested in because every option has cv dt. So let us look at the options. So option D is the same as this. So option D is one of the correct answer. But now wait, we can relate this to the following using the Maxwell's equation. So option B is also one of the correct answer. Problem number 95. 540 gram of ice at 0 degree Celsius is mixed with 540 gram of water at 80 degree Celsius. the resultant temperature of the mixture would be. So let us first calculate the heat required to melt the ice. So this is equal to 540 gram times the latent heat, that is 334 joule per gram, and this is 180360 joule. And now we calculate the heat released by the water, that is 540 gram times the specific heat, that is 4.2 joule per gram per degree Celsius, times 80 degree Celsius, and this is 181440 joule. Since these two are same, so the heat required to melt the ice will be provided by the water. So essentially the temperature will be 0 degree Celsius. So option A is the correct answer. Problem number 96. What is the minimum attainable pressure of an ideal gas in the process given by this? So we use the ideal gas equation, PV is equal to RT, and replace T by this A plus B V squared, or P is equal to R A by V plus R B V. Now let us take the derivative with respect to V, and this is equal to minus R A by V squared plus R B. Since we need to find the minimum pressure, so we will equate it to 0 and find the value of V, and this is equal to square root of A by B. Now let us find the minimum value of the pressure. P is R A divided by square root of A by B plus R B square root of A by B, and that is R times AB and twice of that. So option C is the correct answer. Problem number 97. According to Debye's theory, the phonon mode of density for two-dimensional solid will vary with the frequency as. So the density of states d of omega d omega is proportional to d of kx d of ky, that's the infinitesimal area in k space for 2D solid, divided by the area for each state. So now we convert this to polar coordinate, that is k dk, and use the relation omega is equal to v of k. Thus this becomes omega d omega. Thus d of omega d omega is proportional to this, or d of omega, the density of states, is proportional to omega. So option A is the correct answer. Problem number 98. In case of Bose-Einstein condensation, the number of particles increases in lower energy levels at low energy and high pressure. So option A is the correct answer. Problem number 99. The density of a quantum system with 2 microstates is given by this. Choose the correct option. So we have rho is equal to 2111. So trace of the rho is 3. Thus we can normalize rho as follows: 1 by 3, 2, 1, 1, 1. To calculate the expectation values, let's say sigma z, we use the following formula, that is this times sigma z. Thus we multiply rho and sigma z first, that is 1 by 3, 2, 1, 1, 1 times 1, 0, 0 minus 1, and that is equal to 1 by 3. So we only calculate the diagonal entries here. So this is 2 and this is minus 1. So the trace is 1 by 3. Similarly, we calculate rho times sigma x, and this is 1 by 3, 2, 1, 1, 1 times 0, 1, 1, 0, and again we calculate the diagonal elements. So this is 1, 0, 1, and this is 1. So the trace would be 2 by 3. So option C is the correct answer. Problem number 100. Consider a system of n weakly interacting particles at sufficiently high enough temperature T. Suppose the restoring force acting is proportional to x to the power 5. Then the heat capacity at temperature T will be, so the force is like x to the power 5, thus the potential will be x to the power 6. The Hamiltonian would look like p square by 2m for one particle plus k x to the power 6. So in general, a term like x to the power s will contribute to the heat capacity kb by s. Thus the contribution to the heat capacity from this term will be kb by 2, and from this term will be kb by 6, and that is 2 by 3 kb. Since there are n particles, we have kb times n times 2 by 3. So option D is the correct answer.